the summary place. All right, so we are here last time. Last time, so at this point, what we are doing? Now, we want to improve our brute force method. Brute force method, first we know it's not the best one. Because we find a simple example, we can do better than the brute force method. Yeah, remember x to the fourth. That one we can do better than the brute force one. Yes, it's not the best. Yeah. All right. So now we try to find the best. Yeah. We try to find the best. Yeah. Or much better one. Yeah, because the best you need to show, later you will see you need to show why this one is the best, right? Yeah. So that will be very hard. How can you show your algorithm is the best, right? Yeah. Yeah. When we try to find a more efficient algorithm to evaluate polynomials, we start with a simple, meaningful case. Yeah. So let me change the pen color. Okay, yeah. Simple but a meaningful case. N equals 2. Simple, meaningful. Yeah. N equals 0 and 1, although simple, but not very helpful. Basically, we can do nothing. Okay? Yeah. Yeah. Too simple. No room for manipulation. Yeah. So we choose this N equals 2. Yeah. And the gain is obvious. We reduce the number of multiplications from 3 to 2. Lot of improvement. So that tells us this is the right direction to go. We should keep going along this direction so we can get much more improvement. Yeah, so that's the next step we want to do. Keep doing using the same idea, same approach. We want to do much better. Yeah. Look at the summary. In the summary, we change the order of operations by factorization that results in better efficiency. So we want to do the same thing when n takes larger values. So let's go to the next step. Do some more work in order to understand our method. So here, another point I like to convey in problem solving. Here we are doing problem solving. Another point I like to convey. When you do problem solving for these computing problems, how well you can do, it relies on how well you understand your problems. If you can understand your problems better, then usually you can do better. All right, yeah. Understanding, very important. Yeah. All right. After we work on special example n equals 2, we get some understanding, right? Yeah. Here, in order to strengthen our understanding a little more, let's work on another special example. Yeah. So give us better understanding. Yeah. One more special example. Yeah. N equals 3. Yeah. Another simple example, 3. So let's see if we can apply the same idea effectively for this new case. Okay, all right. This time, let's write a cubic polynomial. So this is cubic polynomial. Okay, one more term than the previous one. Yeah, all right. Key to the success. Let's recall why our method is quite successful in the previous time. Key to the success. What's that? factorization, because we applied this technique, factorization technique. So that changes the order of basic operations, additions, multiplications. Yeah. Our decision here, we want to take advantage of this factorization technique. How do we apply this factorization technique for this new case, cubic polynomial case? All right. The factorization should cover as many terms as possible. That's based on our understanding, because the more terms the factorization can cover, then we take advantage more from factorization technique, right? Yeah. We know it's a good one. It helps us improve the efficiency, so we want to, make it cover more terms, so we can improve more. Yeah. So that's based on our understanding. So this is so-called understanding. Okay? Yeah. Part of the understanding. Yeah. All right. This time we rewrite the expression for the cubic polynomial, but this time, look at the factorization, we cover as many terms as possible. Only the first term we cannot cover. Okay? The first term, a0, it does not contain the common factor x. So we leave it out. Other than the first term, constant term, all terms, they have the common factor x. So we can factor it out. Yeah. So that's what we mean, apply factorization on as many terms as possible here. Okay? All right. Yeah. Yeah. Then, after our first round factorization, let's look at inside the parenthesis. Inside parenthesis, we have a shorter expression, right? Some shorter expression inside parenthesis. Although it's shorter, it has 3 terms. It has 3 terms. Yeah. If we only focus on these 3 terms, can we apply factorization another round? Second round. Because we can still observe some certain terms with common factor. Okay? Yeah. Yeah. So now let's apply factorization second round. Yeah. Because each round, when we apply factorization, we can save some operations. Yeah. So that's why we want to, apply factorization technique as much as we can. Yeah, that's the point. Yeah. So the second round, you can see, other than the first term, the second and the third, we can factor another x out of it. Yeah. Second round factorization. Right? Yeah. See? Yeah. In this way, that's the best we can do by applying factorization. The best we can do. Okay? All right. Yeah. So now we can do no more. Yeah. So that's all we can do. Yeah. Let's do the counting. Let's count the number of multiplications in this new expression. Yeah. All right. Yeah. So here you can see the strategy. We apply certain method as much as possible. Yeah. So later I will come back to this point. Yeah. Now I want to count the number of multiplications in this. Yeah. Yeah. So yeah, the other one, yeah, we will look at later. Yeah. Let's count. 1 multiplication here, second multiplication here, third multiplication, right? Yeah. So the total, 3 multiplications. 3, okay? Yeah. All right, yeah. For the comparison, if we do not do factorization, let's look at the number of multiplications in our brute force method. In the original expression, you have 1 in this term, you have 2 this term, 3 the last term, you add them together, total 6. Now look at the improvement. The improvement is from 6 to 3, 1/2. Remember the previous one, the previous case, from 3 to 2. Less than 1/2, right? This one, 1/2 reduction. Reduce the original multiplication number 6. 1/2 of it is gone, cut off. Okay? Yeah. The previous one, 1/3 of it is reduced. This one, 1/2 of it reduced. You can see when the degree is higher, our reduction is also higher. Reduction portion also higher. Okay? Yeah. So we can keep doing better and better if we do this way. Okay? Yeah. Think about that. All right? Yeah. Now, the summary part. Yeah. Yeah. Here, we apply factorization as much as possible. Yeah. This kind of strategy we will use in many other places. Some effective, good technique, we want to apply it as much as we can, just like in this example. Yeah. So this approach, we have a special name for it. We call the greedy algorithm. Greedy algorithm. Yeah. Yeah. Because, simulating from our real world experience. Yeah. Try to be greedy here. Okay? Try to get as much as you can. Yeah. That kind of greedy. Okay? So we call it greedy algorithm here. Yeah. Question?
So it just means applying the method as much as possible, the greedy algorithm?
Yes. Yeah. All right. More specifically, as much as possible, yeah. I need to add one more special point. Apply as much as possible locally. That's locally, not globally. Yeah. So you will see the difference. Yeah. I will talk about this local versus global later. Okay? Local versus global later. That's a key property of this greedy algorithm. Okay? Yeah? Yeah. So I'll delay it a little bit. Yeah. All right. The idea, push this method to the general case. Now, we feel we are ready to work on the general case, end case. All right. Yeah. Strategy for the general case. For generalization, do factorization as much as we can. Greedy algorithm. Okay? Again. All right. Greedy idea, greedy approach, greedy strategy. Yeah. Yeah. So that's one part, one topic of our chapter 7 or 8. Yeah. Very late chapter, greedy algorithm. Yeah. Yeah. But we may not have time to cover that chapter, all right, in the textbook. So I want to talk about this greedy as early as I can. Yeah. 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 Because our time very limited. So many chapters we cannot cover in this textbook. Yeah. Yeah. But I try to find chances to cover some of the important ideas earlier. Yeah. All right. Now let me talk about that local global thing, greedy algorithm. Yeah. Apply some property as much as we can at each step. Remember, each step, each factorization step, we apply the greedy, apply factorization as much as we can. Each step, all right? So here I emphasize this, each step. Yeah. Let me explain why. Each step, we treat it as local application of the greedy algorithm. Yeah, because only one step. You do not look at other steps. You only focus on the current step. That's a local focus, right? Yeah. You work locally. Okay. What's the globally? You consider all steps. That's the global. You cover all the steps in this algorithm. That's globally. Okay? Yeah. But for greedy algorithm, we only apply the greedy strategy locally, not globally. Okay? Yeah. So that's the main property of this greedy algorithm. Main property. All right? Yeah. So you may ask me why, right? Yeah. You may ask me why we do not apply greedy strategy globally, not locally. Yeah. The answer is very simple, because too hard. How can you apply greedy strategy globally? Yeah. How well? Yeah. We as a human, okay? So our logic reasoning, we have very limited logic reasoning capability, right? Think about, okay? Think about playing chess. How can you compare with AI? Nobody can compare your chess playing capability with AI. Why? Because AI can do computation in a relatively global way, right? Yeah. The computation compute 30 levels, 40 levels. The more levels, more global, right? Yeah. How can we do the logical reasoning that many levels? We cannot, right? Yeah. The grandmaster, you can do 10-something levels, right? Then you will get lost. So we couldn't. Yeah. Here, the greedy strategy also the same, because we cannot do globally. Yeah. We're not able to do it. So what we can do locally, okay? Easier, much easier locally, yeah, yeah. But the result won't be as good as the global way, okay? Global way, your solution would be better. The local way, sometimes it's good, sometimes it's not good. Okay? Yeah. Try to get that point on the greedy algorithms understanding. Okay? All right? Yeah. A greedy algorithm is locally optimal. Yeah. The best we can. Yeah, we want to make it optimal. Okay? But it's a local optimal property. Yeah, not global optimal, because it is easy to achieve. Yeah, all right. It may not be optimal, globally it may not be optimal, because it could be very hard to get an optimal solution. Yeah. When you work on a very complicated computing problem, here let me give you an example, one famous example called traveling salesperson problem. You may have heard of it. TSP, traveling salesperson problem. That's the famous, very difficult MP problem. People also call it MP problem. Extremely hard. Yeah. Yeah. You can apply some greedy strategy to get a local optimal solution, but it's far away from the globally optimal solution. Global optimal solution, nobody can find it. Yeah. Too hard. That's why it's an MP problem. Okay? Yeah. This class, this is an undergraduate algorithm class. So we won't go that far. The MP complete problem, that's the graduate level content. Okay? MP complete. Yeah. Traveling salesperson, many other graph coloring problem. Yeah. So, many famous MP problems. Yeah. Yeah. But this one, yeah, it's an undergraduate level. Yeah. So we won't get, go too far. Yeah. All right. Now the general polynomial with the pattern. This time, don't throw away our experience when we work on n equals 2 and 3. It's very valuable. So we should use the basic point, basic structure from our previous 2 experiments and do the best we can here. All right? Yeah. Look at it. Cubic polynomial, the factorization pattern we have. The structure, the pattern we have here. Okay? So we want to do the same thing. Yeah. Using this example as the model, we want to do the same thing. Yeah. As a result, we keep do factorization round by round. Okay? Step by step, level by level. At the end, we get a factorization like this. That's the best we can do here. We push to the limit, right? We push our ability to apply the factorization technique to the limit. No more we can do, all right? That's all we can do here. Yeah. Already to the limit, okay? Yeah. Then do the counting. How many multiplications do we need here? Do the counting. Can you find some good way to count the number of multiplications? We have similar experience before. Here we just need to repeat our previous experience. How many multiplications do we need? Here, how many?
Would it be n?
Correct. It's n. N multiplications. But can you give a solid explanation on why we get this n multiplications? Not just a guess. So here, we want to have a very solid way to get it. Yeah. What's? Yeah, use exponent, whatever, yeah. But here, I want to refer to one special counting method I gave you before. Remember, let's recall, how did we count the number of additions before? We use a special method, right? Counting number of additions. Counting by reference. Still remember that? Counting by reference. Here, let's apply that counting by reference again to count the number of multiplications here. Here we have the similar situation, comparing with counting number of additions. Yeah. So the similar situation is we have this ... thing that caused some hard time in our counting, right? Because it makes hard to keep track of the data, right? The ... we get lost, how to keep track of the data. We get lost, yeah. And in that situation, last time we got lost, right? Counting, keep track of plus sign, we get lost. Here, not plus sign, multiplication, this parenthesis, here, this place, there is a multiplication. But it's hard to keep track of all these multiplications, right? When we go through that skipping part, we get lost. So we need some tool to help us keep track of the data. Yeah. So by that counting by reference method, let's find some reference objects. Yeah. So what reference object you want?
Well, I was going to say, because and I might be using just we know that like, as far as like real integer variables, we've got
Yeah.
up to a
Yeah.
sub 2.
Yeah.
And then after we see the ellipses, the dot, dot, dot.
Yeah.
So we can assume, well, I'm assuming that we're going beyond 2.
Yeah.
But we don't have a maximum value. The only time we see any value that goes less than another value in there is we've got a sub n. And then before that, we have a sub n minus 1.
Yeah.
So that my assumption was like, okay, well, n might be the highest
Yeah.
value, and
Right.
then we're going backwards from
Right.
there.
That's exactly the counting by reference point. Yeah. Here I just use some formal language to describe this method. Yeah. That idea matches the main property of counting by reference. Yeah. Here, one-to-one correspondence. The first multiplication, can we associate with the first subscript, a sub 1, that subscript, its closest coefficient, the subscript of it? Yeah. The second multiplication, can we associate with A2, its subscript of A2, and so on. So each one, multiplication, we associate with an adjacent coefficient, its subscript, okay? All right, so this one associated with n minus 1. The last one, the last multiplication right here, associated with the subscript of the last coefficient. How about that? Is it a one-to-one correspondence? One-to-one correspondence? Right? One-to-one correspondence, it tells us when we count number of multiplications, that's the same as counting the number of corresponding subscripts. What are those corresponding subscripts? 1, 2, consecutive integers, dot, dot, dot. Here we don't worry about dot, 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 right? Because consecutive integers, we won't get lost, okay? Nobody will get lost when you go through consecutive integers, right? Yeah. So, n minus 1, n. Then count number of objects in this list. Everyone can get a clear answer, right? Yeah. That's the so-called counting by reference. Okay? Here it's the second time we apply this counting technique. Okay? I hope, so after a few times, you get used to it. Okay? Later in the future, so even in a relatively more complicated situation, you can use it this way. Okay? Simple, but effective. You won't get lost. The point is you won't get lost. Okay? Yeah. Yeah. All right. Yeah. Now, the answer, n multiplications, and we call this method Horner's rule, the famous Horner's rule. Okay? Yeah. Pretty simple, but the improvement is huge. Why this method is so good? The improvement is huge. Yeah. How many multiplications are there based on the new? Yeah, so we have that answer, n. Okay, all right. Next, we want to do the comparison. The old method and this new Horner's rule method, we know the second one much better, but can we get a clear visual way to see how much difference? We want to see better. How much is the difference? Okay, yeah. So, 3.4, visualize performance improvement. I'd like you to feel about the difference. How big is the difference? Feel about it. Okay, yeah, all right. Let's look at the difference in formulas. So let's, do side by side, two formulas. Yeah. All right. Here we only look at the multiplications. Yeah. We do not look at the additions. Addition part, both the same, right? And additions. Both methods at the addition part, they are the same. And additions. So now we only look at the multiplication part. Remember the Amdahl's law, I mentioned last time Amdahl's law, when we do the improvement on the system here, some system here, we should focus on the common part. Multiplication is the more common part, okay? Here, we focus on the common part. The improvement is from this many multiplication to just n multiplications. Impact of multiplication reduction. We want to see how big is the impact here. Reduction. All right. It's too abstract. If you just look at from the formula, although you know the difference is big, but still too abstract, right? Because when you look at the formulas, just the symbols, numbers, symbols, you do not have any real world concrete feel about it. You don't have, real world experience. So we want to use our real world experience to feel the difference, not abstract difference. It is better to try out a couple of concrete examples here. So let's do experiments. Let's do a couple experiments to let us feel about the difference of these two methods. The first experiment, so let's try n equals 1,000. 1,000 degree polynomial. How many multiplications do we need when we have a degree 1,000 polynomial? Based on old formula first, new formula just 1,000 multiplication. The old formula, when we plug in, here I use a approximate number, okay? Not exact, approximate. 1,000 approximately 1,500, right? 500 multiply 1,001, here I just multiply 1,000 because that answer much easier to see. So you have 500,000 multiplications by the brute force method. The difference is already big, right? 500,000 versus 1,000. How big is the difference? Okay, the ratio is 5,000 to 1 ratio. Is that pretty significant? 500 to 1. Not 500. 500 to 1 ratio. Much less than 1%, right? 0.2%. Okay? New method only takes the amount of time that is 0.2% of the old method. You do the same thing, but new method, 0.2%. How big is the improvement? Right? That's our first experiment. Here I'd like to show you the second experiment. The second, this time, let's consider 1 million degree polynomial. 1 million degree. So you can imagine, this polynomial is so big. Do we need to consider a polynomial this big in the real world? You don't know, right? In the real world, especially at this time, it's the, big data time, right? Big data era. So you can imagine the scale of amount of data huge, just a 1 million degree. That's very possible, right? You may need to deal with this large data size in your real world applications, right? So let's try our second experiment on 1 million n degree. Yeah. This time, new method, we need 1 million multiplications. Yeah. But the old method, after you plug in, here we still use approximation. Yeah. What do we have is this large number. Yeah. Can you tell me how large is this number? So can you give me a name of this number? How do you call this number? 500. What's the name of that one? Counting. Yeah, good. 500 billion. That's correct. Okay, 500 billion. Yeah. Now let's take the ratio. The ratio is 500,000 to 1 ratio. 500,000 to 1 ratio. How big is that difference? Old method, new method, especially when we work on the large data size, the difference is so big. Yeah. Here you can already see such a big difference, but I like to use another way to let you feel the difference, more impressive way to feel about the difference. Yeah. That difference is, how about for the new method, this 1 million multiplication, let's imagine we just need to use 1 second to complete 1 million multiplications. Okay? 1 second. Yeah. Some supercomputer, we can do it in 1 second, right? 1 million multiplications. Yeah. Quite reasonable. Yeah. But if we use the same computer to calculate the same polynomial, but using the old algorithm, the brute force one, that number should be multiplied 500,000 times. So you need to use 500,000 seconds. How long is that? 500,000. Let's do the conversion, converting to number of days, so we can see better. Yeah. Seconds, we have no idea how long it is, right? We know it's quite long, but how long? We have no idea. Yeah. Let's convert it to the number of days, 5.8 days. Now you have an idea, right? Almost 6 days. So you can see the big difference. Our new algorithm, after you hit the enter, after 1 second, you get the answer. The old algorithm, you work on the same computer, you hit the enter, you need to wait 5.8 days. Then when you come back to see the answer. But the same answer. Is that a big difference? Yeah. So here you can see, in the real world situation, we want to get a second solution. We don't want to have the first solution. Okay? Yeah. Because when you need to develop a business solutions for your customers, yeah, so you can imagine some special computing task. So your customers pay you to develop business solution for it. Okay? So you want to use the best algorithm. Okay? Yeah. So there is some good algorithm like this Horner's rule, and there is some bad algorithm like the brute force method. Okay? Yeah. So you want to make your solution, at the end, you want to give your customers this Horner's rule, this fast, the solution like our second one, not the first one. Okay? So the second one, so when finally, when you want to deliver the solution to your customers, when you show, so you are very confident, right? Because after you hit enter, your customer can see the solution immediately. But you don't want to bring the first solution to your customers, right? Yeah. Yeah. Because it's not acceptable. Even if the solution is correct, it's not acceptable. Right? 5.8 days. So your customers won't pay. Okay? That solution, that bad solution, so your customer won't pay it. Okay? Yeah. So you can see the huge difference. Right? Yeah. In our first programming project, we will work on this topic. Okay? Yeah. So I want you to write your own program to see the difference. The first one, you need to wait very long. Yeah. But I do not let you wait 5.8 days. Okay? So that's ridiculous. Yeah. I just let you wait 30 seconds. 30 seconds, is that long? 30 seconds? Is that long? 30 seconds? Yeah. Right. When you sit in front of a computer, 30 seconds, you will see extremely long. Yeah. Because our expectation, when we run a program, we expect result immediately, right? 30 seconds, that long waiting, that's rare. Based on your experience, it's rare, right? Yeah. But you will see it. The first algorithm, I let you wait about 30 seconds. Okay? Okay? All right? Yeah. Yeah. Even 10 seconds, that's very long. You can imagine. 10 seconds, that's very long. Okay? Yeah. All right? Yeah. So we finish this topic. Yeah. And we can work on our first programming project. Yeah. I will give you the description. Yeah. Actually, I want to add 2 more components. Yeah. So I haven't really complete those 2 extra components. Yeah. After I finish 2 more components, then we can start work on our first programming project. Okay? Yeah. All right. Any question? Yeah. 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 So let's move to part C. Yeah. Yeah. And in this one, yeah. So here, this one, I also include made several flashcards. Okay? Yeah. So here I show you, a few flashcards. This part, because the material, we have much more material than part A. Part A, we only have 3 flashcards, right? Here, yeah, look at all these flashcards, all right? Yeah, Amdahl's law, right? Yeah, so I have, 14. Yeah. Yeah. 3 from part A, yeah, 11 from part B, so total 14 flashcards. Okay? Yeah. Yeah. So you can use these flashcards to help you understand the main points, the important knowledge points in the material. Okay? Yeah. And when I create questions for your quizzes, homework, and tests, I try to focus more on these flashcards. Okay? Yeah. I practice based on all these flashcards. Yeah. Try my best. Yeah. Okay? Yeah. All right. Yeah. So let me get out. Title: Role of Data Structures in Algorithm. Yeah. All right. C.1. Search unordered arrays. Here, I want to, address the point. Data structure, its role, very important in our algorithm design, especially for advanced, complex algorithms. Many times, we need to rely on advanced data structures. Yeah. All right. Problem number 2, search an unordered array. Yeah. Given an unordered array, we use this representation, and a search key K. Find an index I such that K equals A of I. The search question, as simple as this. Here, the problem type we're looking at, the search type. In this class, we have 3 basic problem types. Search type is one, sort, another basic type. Then selection, another basic type. These 3 basic types of problems, computing problems. All right. The data structure we used here, simple. It's array. Simple. The simplest possible data structure, array. Here, I give you the reference. So we go to section 2.1. All right, the material. You can, if you want to read the material, so you can go there. Question, why the data structures are important in algorithm design? So the basic point here is, through data structures, we can make our data well organized. Let's recall in our first lecture, part A, when we work on the chessboard question. Our data, so all those squares of different sizes. So we did one thing, organize our data, right? Here you can see we want to make our data well organized. So we can find our data faster. If the data is organized, we can find the required data faster. Okay? To save time. All right. Find the required data faster. So that's the reason. We are willing to spend time to organize the data. Organizing the data, that step, we can treat as pre-processing. Organize the data, we need to spend some time, computing time. All right? But we call it pre-processing. The reward is big. After you pay that amount of time to get your data organized, the benefit also big. So later you just enjoy the benefit, the good properties in your data. So you will see that later. All right. Get a better performance. That's our goal. Okay? Let's do analysis. Basic operation in this question. Search. Here, remember another important property of our data, it's unordered array. So that's a, important property here. Okay? So don't forget this property. Unordered. All right. So the basic operation is comparison. You need to compare. Okay? So the given key value with your element value and see if they are the same or not. That's the basic operation here. All right. Compare K and A of I. I index. So you want to go through all the elements in the array. When you start with the first element in the array. So initially, I equals 0. After that, so you compare K with the value of the current element, A of I, value of current element. So you only have here, we only consider 2 different states. One A equals A of I. Another A is not equal to A of I. Different. Not equal, we do not need to know greater or less. Although if you want, you can know greater or less. But it's not important, right? So we don't care, greater or less. Just different. Different. Then we want to move to the next one. Okay? So it is, if equal, we find it we find the right element in the array, so we return the position of this element. That is the index value I. Then we're done. Okay? Yeah. But if not equal, we need to do more work. Other iterations. Yeah. So for a typical iteration, next iteration we compare k with a of I plus 1. Okay? Yeah. Then you want to see equal or not equal. Yeah. But at the end, sooner or later you will reach the last element. Last element, that's the I value equals n minus 1. If you cannot find one that equals the given element, that's possible, yeah. Then you make your function return -1 value. Yeah. Yeah. The reason is simple. Yeah, why -1? Yeah. Because in the normal case, you return the index value that tells the position index in the array. If you do not find it, you should not return a valid index of an array element. So you want to return a value that's not a valid index. Here we choose -1. We know -1 is not a valid index. So if you see this value, you can get the idea the given element cannot be found in the given array. Yeah. So that's all we need to know. Okay? All right. So we complete this simple algorithm. Yeah. The implementation is simple, very straightforward. Yeah. Here. We want to look at the analysis part. Yeah. So for this question, yeah, our main focus, we want to put on the analysis part. Yeah. Yeah. All right. The algorithm, we call it sequential search or linear search. Yeah. So many people also call it linear search. Yeah. Sequential, because you follow the natural order of the given elements sequentially, yeah, in a linear way, in a line, right? Yeah, sequence, line, in order. Yeah. So the linear search. Yeah. So that's the name of it. Yeah. All right. Next, we want to look at the efficiency of the algorithm. Yeah. To do. Yeah. So what we need to do here, we want to count the number of comparisons. Basic operations. How many do we need? Yeah. All right. Here, let's look at all the possible cases. We list all the possible cases when we apply this algorithm, linear search. Yeah. So you can see, yeah, total, there are n plus 1 different cases. The first n cases, the key can be found in the given array, but there is last one. The key cannot be found. Yeah. So total, n plus 1 cases. Yeah. So now, we want to look at the specific number of comparisons for each case. The first case, the first element equals the given key, you only need to do 1 comparison. If the second element equals the given key, so you only need to do 2 comparisons, and so on. Okay? The last one, n comparisons. And there is no match case, the last matching case, okay? The last match case, n comparisons. The no match case, also n comparisons. Yeah, all right. Yeah. Yeah. So we know the number of comparisons for individual cases. Yeah. All right. Now we want to know another important information from this question. Because there are n plus 1 different cases. The question, what is the overall efficiency? We want to tell people, if people ask you, what's the overall performance of your algorithm? Okay? Yeah. So you want to use one number to describe its overall efficiency. And this number should be a fair one. Yeah? Fair one under some criteria. It's fair. Okay? Under some standard, it's fair. Yeah. Because here we have the best case. The first number, one comparison, it's the best case. Do you feel this number is a good one to describe the overall efficiency? If you just tell people your algorithm, one comparison, that's not a good one, right? Not a reasonable, fair one. Okay? Yeah? Because too good. Most of the time, you couldn't get this efficiency. All right? Yeah? So it's not a good one. If you use the worst case, and comparisons, yeah, to describe the overall efficiency, do you think it's a good one, reasonable, good one for overall efficiency? Yeah. Right? Yeah. Yeah. Because if you use this one, most of the time you do better than this one, right? This is the worst scenario, worst case scenario. Yeah. But for the general, ordinary cases, you can do better. Yeah. So if you use this worst case number, you're too pessimistic. Okay? You're too pessimistic. Yeah. So that's also not good. Still not good. Okay? So you really want to use a fair one. Okay? Not too good, not too bad, some number in the middle to describe the overall efficiency. Yeah. So something in the middle, so people usually use average number, right? Average. Yeah. So most of the time people use average. Okay? Yeah. And here we have similar concept, yeah. Average case efficiency. When we talk about overall efficiency, we like to use the average case efficiency. Not the best case, not the worst case, it's the average case efficiency. But the hard part of the average case, how do you clearly define the average case? Because for the best case, we know its meaning easily, right? For the worst case, we know its meaning easily. But what's the meaning of the average case? What kind of average you are talking about? Yeah. Is there a fixed meaning of average all the time? There are many different average meanings, right? Yeah. If you recall, people use different meanings of average in different situations. Yeah. So here, what specific average you are talking about here? Okay? Yeah. So we want to make that clear, clarify the meaning of average. Okay? Yeah. So the average should include all these n plus 1 cases. Yeah. You cannot miss anyone. Okay? If you miss even one of the cases, your average is not the best. At least not the best. Okay? All right. How to know all the cases? Here we need to, really get more information about all these cases. Okay? Yeah. Here we put it in this table, all the n+1 cases. Yeah. But you will see we need to know more information regarding these n+1 cases. Yeah. Another question is how to combine all the cases. We need to find a way to combine all the cases. Yeah. There are many different ways to combine all the cases, right? Yeah. Many different ways. Yeah. All right. We need to make appropriate assumptions. Here, in order to use some reasonable way to combine all the cases, we want to make some reasonable assumptions here. Yeah. So what's the assumptions? Yeah. We want to make, fair assumption. Yeah. Yeah. Corresponding to the real world situations. Yeah. So that should be what we really do in the real world. All right? Yeah. C.2, let's look at the average efficiency. How to combine all these n+1 cases. Yeah. All right. Let's make assumptions. Yeah. The first assumption. Yeah. For the first n cases, we want to assume that these cases have the same probability. For the probability assumption, okay? Yeah. Equal probability to get first case, second case, third case, each one, same probability. Okay? Yeah. Yeah. So that's the first assumption. Because we have no information. Which value has more probability? We don't know that. Yeah. So if you do not have any information, you just assume their probabilities are the same. Yeah. Second assumption. How about the no match case, the last case? No match case, you cannot assume it has the same probability with any of the previous cases. You cannot assume that, right? Not reasonable. Yeah. You need to consider the real world situation. Most of the time, you won't have that. You cannot assume the same. You cannot make the wrong assumption. Okay? Yeah. So here, we have to make the right assumption. Yeah. So here we assume the probability for the index case. That means the key can be found in the given array, the index case. Your function returns a valid index value. That's the index case. That probability here we assume is a p number, certain p number. The p is in the range between 0 and 1. So we know that's the probability range, typical probability range. Okay? So that number should be known. When you do the calculation, that p number should be known. Yeah. So you may ask, how do we know that number, right? How do you know that p number? By experiments in the real world. Yeah. You need to, run linear search on many sample data. Okay? Yeah. So you need to do experiments, a lot of experiments on sample data. Yeah. So based on your sample data, so you can get an approximation of this probability p. Yeah. So you just use that p to, simulate the real world situation. Okay? Yeah. Assume you have this p number. Yeah. Then the -1 case, no match case, the missing case, 1 minus p. because the total of all the cases should be, the probability total should be 1. Yeah, because here these two cases complement each other. Yeah. So just 1 minus p for the no match case. All right, yeah. Under these two assumptions, now we are ready to calculate average case efficiency. Yeah. So let's do that calculation, yeah, before we finish the lecture today. Okay? Yeah. Let's do it. Yeah. Yeah. How to get, we are here, I already told you, do statistics based on the history data. Okay? Yeah. So you have history data. Okay? Sample data, history data. Yeah. So, all right. Or we can do dynamic statistics. Yeah, there is another way. Yeah. Because you apply this linear search algorithm on the fly, right? Yeah. So data keeps coming in. Yeah. Apply this algorithm on the fly. Yeah. On the fly, you can do dynamic statistics, right? Yeah. Yeah. Because you have all the history data, you just do statistics. Okay? Yeah. So you have that p. Yeah. It's, that's another way to get this p. Yeah. All right. Yeah. Then, now we can do our goal, average case efficiency. How to combine these n cases. Yeah, this time, we're ready to do that. Okay? Yeah. All right. So we look at it as two subcases. The first subcase, that's the index case. So we put them together. Yeah. We can calculate the average for the first subcase first. Yeah. Then, no match case, we treat it as the second subcase. So we can do average for these two individual subcases first. Okay? Yeah? Yeah? All right. Yeah. All right. Yeah. For the first subcase, yeah, based on our assumption, the average, just the standard average, adding up all these comparison numbers divided by n. Yeah. That's the average number of comparisons for the first subcase. Yeah, so simple. Yeah, based on assumption. Yeah, all right. Yeah. Second, its average case also simple because it has only one. No match case, only one case. You do average on one case, the same number. Yeah. So for the second, if you look at its average of one number, it's the same number. Okay? Yeah. All right. Next question. How do you combine these two numbers? Yeah. So the last one. These two numbers, when we combine, we use another special energy we called weighted average. Weighted average. Okay? So what's the weight? The weight of the first case, that's p. The weight of the second case, 1 minus p. Its corresponding probability, we call it its weight. When we do the average, we take the weighted average in this standard formulation. Yeah. Yeah. Individual average number multiply its weight for each subcases. Then we add them together, add them up. All right? Yeah. So that gives us the overall average case. Okay? That's the final formula for the average case efficiency. All right? Yeah. Okay. Yeah. So that's what we want to derive for this simple algorithm. Yeah. After this one, you should get a better understanding on average case efficiency. the main idea, how to calculate the average case efficiency. Okay, all right. Yeah, we run out of time. Let's stop right here. The next time, let me make some summary for our discussion so far. Okay, so then we move to the next topic, the summary. All right.